10 black hole theories that still disturb physicists. 1. The information paradox. Physics treats information as permanent. Particles can change form, move through space, or interact with other particles, but the information describing them should always survive somewhere in the universe. Black holes complicate that idea. Anything crossing the event horizon disappears from the observable universe entirely. According to Stephen Hawking's calculations, black holes also lose energy over enormous periods of time through Hawking radiation. Eventually, the black hole itself may vanish. That creates a serious problem for modern physics. If the black hole disappears, what happens to everything that fell into it? Does the information survive in some hidden form? Does it leak back out somehow? Or is information truly destroyed forever? Physicists still do not agree on the answer. The contradiction sits directly between quantum mechanics and general relativity, two of the most successful theories ever created. 2. The firewall theory. For many years, physicists believed the event horizon of a black hole would feel physically unremarkable to someone falling through it. The tidal forces deeper inside would eventually become fatal, but the boundary itself was expected to behave normally. The firewall theory changed that assumption. According to this idea, the edge of a black hole could contain an extremely energetic barrier of particles and radiation. Anything touching it would be destroyed instantly. The proposal emerged from attempts to resolve the information paradox. Some calculations suggested information could only remain preserved if the event horizon itself became violently unstable. If the theory is correct, black holes are surrounded by a region capable of vaporizing matter before it fully enters the interior. 3. White holes. General relativity allows equations that describe a strange hypothetical object known as a white hole. A white hole would eject matter and energy outward continuously. Nothing would ever be able to enter it. No confirmed white holes have ever been observed. Even so, the mathematics behind them continues to appear in certain solutions to Einstein's field equations. Some researchers have explored connections between white holes, wormholes, and the early universe itself. In certain models, matter entering a black hole could emerge somewhere else through a white hole-like structure. The idea remains speculative, though the possibility continues to appear in theoretical physics. 4. Primordial black holes. Most known black holes form after massive stars collapse. Primordial black holes come from a very different idea. According to this theory, black holes may have formed during the earliest moments of the universe, long before stars or galaxies existed. Tiny fluctuations in density after the Big Bang could have compressed certain regions enough to create microscopic black holes. Some may have evaporated billions of years ago. Others may still exist today, moving invisibly through space. Researchers have even investigated whether primordial black holes could account for part of dark matter. If that theory is correct, ancient black holes from the beginning of time may still influence the structure of entire galaxies. 5. ER equals EPR. ER equals EPR is one of the strangest ideas proposed in modern theoretical physics. The theory suggests a connection between quantum entanglement and wormholes. Quantum entanglement allows particles to remain linked across enormous distances. Changes affecting one particle influence the other immediately. Einstein strongly disliked the implication and referred to it as spooky action at a distance. The ER equals EPR proposal suggests entangled particles may be connected through microscopic wormholes hidden beneath space-time itself. If the idea is correct, space-time may emerge from deeper quantum structures that are normally impossible to observe directly. Black holes may provide some of the first clues about how that hidden structure works. 6. Fuzzball theory. Black holes are usually described as containing a singularity, a point where density becomes infinite and the known laws of physics stop functioning properly. Many physicists remain uncomfortable with infinities appearing in physical theories. Fuzzball theory attempts to remove the singularity entirely. Under this model, black holes consist of enormous tangled collections of quantum strings occupying the entire interior region. The black hole would still appear normal from the distance. Its internal structure, however, would be radically different from the traditional picture. Some versions of the theory also attempt to resolve the information paradox without requiring singularities at all. 7. Black holes creating universes. Some theoretical models suggest gravitational collapse may trigger the formation of entirely separate universes. Under these ideas, the black hole could become the starting point for a new expanding region of space-time disconnected from our own. That possibility leads to a larger question. Our universe itself may have originated inside a black hole belonging to another universe. If so, every black hole forming in our cosmos could potentially create additional universes beyond observational reach. The full idea remains speculative, though variations of it continue to appear in cosmology research. 8. Gravastars. Some physicists have proposed alternatives to black holes themselves. One of those alternatives is the Gravastar, short for gravitational vacuum star. According to this idea, collapsing matter never fully forms a singularity or complete event horizon. Quantum effects halt the collapse before reaching that stage. From far away, a Gravastar could appear almost identical to a black hole. Distinguishing between the two may be extremely difficult using current observations alone. The proposal remains hypothetical, though it continues to attract interest because it avoids several major paradoxes associated with singularities. 9. Naked singularities. The event horizon hides the singularity from the rest of the universe. Some equations in general relativity suggest situations where that boundary may fail to form completely. The result would be a naked singularity, a region where gravity becomes effectively infinite while remaining exposed to the outside universe. Physicists still debate whether naked singularities can physically exist or whether nature somehow prevents them from forming. If they do exist, current physics may lose predictive power near them entirely. The mathematical behavior of spacetime becomes unstable under those conditions. 10. The holographic principle. The holographic principle began as an attempt to understand black hole entropy. Researchers discovered that the amount of information associated with a black hole appears connected to its surface area rather than its volume. That result produced a surprising implication. The universe itself may store information in a similar way. Some versions of the theory describe three-dimensional reality as information encoded along lower-dimensional boundaries. Under that interpretation, space-time behaves more like a projection than a traditional physical structure. Black holes played a major role in developing the idea, and they remain central to ongoing attempts to understand it.